Hi, Julia. Welcome to the podcast.
Hi, Robin. So nice to be here.
Let's begin with where you work and what you do.
So I'm a PhD student at Leiden University. I study computer science, and I work together with atmospheric scientists at Space Research Organization Netherlands. Um, and we work on machine learning pipelines to find atmospheric gases like methane.
Right. So methane detection is kind of a big topic at the moment. What's significant about methane?
So methane is a very strong greenhouse gas, but it only stays in the atmosphere for a relatively short time compared to CO2. So any methane we can avoid emitting right now could make big impacts on our on global warming on
Hmm.
a short time scale.
Great. So how is your research connected to that?
So I design machine learning pipelines for plume detection in the data of a very specific instrument, TROPOMI, on a
Mm-hmm.
board of Sentinel-5P. And this is a spectrometer that measures concentrations of different gases. It looks very different. If you look at the images, it looks very different from optical instruments like Sentinel-2, which is much better known. So it has its own quirks and requires separate pipelines.
Right. Can you briefly describe what a typical image might look like and how it differs?
Yeah, so one pixel for methane is about 5 by 7 kilometers. Um, so if we're looking for methane point sources, that sometimes can even be a whole city at
Mm.
that scale. Um, so there's just one channel, and the channel has like methane concentration, but the satellite data product also has other fields that I use
Mm.
with auxiliary information like cloud masks, surface pressure, albedo, that kind
Mm.
of information that is used in the retrieval of the methane concentrations from the light spectra that are measured.
Mm.
And sometimes when a piece of land has very high reflectivity, then this can lead to errors in the retrieval. So then it might sometimes look like there's a methane plume when there's not. But in fact,
Mm.
it's grainy is not the right word because it's pixely image.
Mm.
Very low resolution, but high spectral resolution.
Right. So you might even have just like a single pixel that's telling you there's a plume.
Sometimes, yes, those are tricky.
Incredible. It sounds very challenging. How have you gone about detecting them?
So the atmospheric scientists I work with already developed a pipeline that confuses divide and conquer approach, first with a CNN to find all the images with a plume-like shape, and then they use the support vector machine with a physics derived features to really discern the real plumes from the artifacts, the things that look like plumes but are not.
Mm.
So I wanted to extend this approach also to other gases measured by TROPOMI. So I wanted to use automated feature extraction, which brings us to neural networks, so end-to-end CNNs.
Mm.
But still, there are differences between the gases. Um, Plumes look at background levels of the gas too. But if you compare, for example, methane and carbon monoxide. So I developed a neural architecture search approach that automatically designs neural networks to find plumes in these different TROPOMI gases.
Interesting. So just so I totally understand, the first network is doing a classification, just saying this image has or does not have a plume in it.
Yeah, so the original approach does as the two steps, and we have bundled this into one.
Mm.
So we have now one neural network that has access to multiple fields of the TROPOMI data product.
Mm.
Well, in the original pipeline, there's the CNN had only access to methane, and then there was a classical machine learning model on top, which would use all the other many other fields from the data product to calculate all sorts of related features.
Mm.
This was very specific to methane, and by designing a neural network that takes a good raster data cube as input, we could generalize this solution to other gases too.
Okay, so going from the two-stage solution to a single neural network, but lots of optimization to find the right parameters for that network.
Yes.
Okay. Do you mind giving us an idea about neural architecture search then?
Yeah, so in this approach, we use optimization algorithm, Bayesian optimization to fine-tune both the architecture and the training hyperparameters of these CNNs that we use for data fusion. And in this neural architecture search, we tweak a few things. So we have designed a backbone CNN that has effectively multiple input branches. So if you have multiple input modalities, so each modality is a different layer from the data product, it gets its own input branch. And the neural architecture search optimizes how deep these branches are and how the branches are then fused in the neural network, and also what the backbone architecture is, because you can have a vanilla CNN or ResNet or even a vision transformer. Um, and the optimization also takes care of the hyperparameters, because when you change the depth of these multi-branch networks, then the optimal hyperparameters can also change drastically. So it's very important to tune those in tandem.
Okay, so you basically define the inputs, give it some range to search over, and it somehow intelligently finds the right parameters or identifies a few different possible solutions.
Yes.
Right, okay. And what are the results like using this approach?
So on the test set, you got really good results of 95% accuracy. Um, this was for methane and similar results for carbon monoxide. So we're very happy with that. But of course, for us, or for me personally, the goal was to make a pipeline that would also be usable in real life. So we also conducted deployment scenario analysis, or use case application, where we took just a week of satellite data, which was only filtered for quality, and there have to be sufficient valid pixels also in each image.
Mm,
And we fed that into our model and we labeled all the images that were detected as plume. So not everything, because there were more or less 17,000 images, and it's not doable to label all of those in a reasonable amount of time. So we labeled the detections and we compared our results with analysis from the pre-existing pipeline to see, like, is this something, this automatically created network, could we use this operationally?
mm,
So there the results were surprising, because methane plumes are very rare, but our data set was mostly balanced because you cannot train a neural network on extremely imbalanced data.
mm,
But in a real world scenario, we did find a lot of plumes, but also about as many artifacts. So the model flagged things that looked kind of like plumes but were not, um, more than we'd like, because that means that in the operational case, the precision was about 50%, 60%, even though on the label test set we got like 95%. So there's a generalization gap there, which of course also comes from partly from the difference in class balances between the data sets.
mm,
And this is issue we're still working on right now, and how to get this gap smaller. Because on the one hand, if you increase the precision, then you might lose too many plumes.
mm,
But if the precision is not high enough, then you have to label a lot of images that might not be plumes. So this is something I'd like to improve in the next project.
mm. And do you think that needs to be addressed in training or in the data? What are you thinking?
Yeah, so we've looked at the data in detail. I think it has to do with the data in some way, because of course we selected, or not me, but the PhD student who made the original data set selected images based on their knowledge of where plumes occur. So there
Mm,
is always some kind of selection bias, even though they selected a very large array of different locations and types of plumes. I suspect there may be some kind of something with sampling going on. So maybe there are some specific types of plumes that we have a lot of in our data sets, but that occur a
mm.
bit less in real life. I think it's something slightly like that.
Okay. So it sounds like you could almost do some kind of investigation to try and understand the different plumes, get an idea of how the different classes of plumes are maybe represented and start to address any imbalances.
Yes, definitely. And now SRON has a lot of knowledge on this because they have been running operational detections for a few years now, where every week there's two different methane analysis experts who look at the predictions of their model.
Mm.
Um, so we are working on this together to see how we can improve the data set for my model. Because I think the key distinction here is that the original data set was designed for this two-step approach. And my model, because it's end-to-end, might require something different, but we're not yet sure what we would need to change about the original dataset.
Fascinating. Just want to cover the architecture search a little bit more. So you had two gases. Did the models end up being the same? Are they different somehow?
They were a little bit different. The same backbones tended to be selected because I found that we included a lot of different backbones. So as I said, very simple ones, just the vanilla CNN, to more complex models. Well, the more complex backbones, like vision transformers, were never selected in the best configurations, and the best models for both gases tended to be the CNNs, which was interesting finding because it's not it kind of contradicts the trend in general computer vision. I think it just has to do with that our data sets are still relatively small and remote sensing data can also be a bit more complex than natural images, smaller features, for instance. So that was part one. And then there was a small difference between the architectures that came out for the two gases. It was mostly the depth of the input branches was different, the ideal input depth.
Right. Okay. Possibly related to the complexity of identifying one gas versus other classes.
Yes, yes, because carbon monoxide is a slightly easier problem because the background levels of carbon monoxide in the atmosphere are lower, so the
Mm.
plumes are a bit clearer.
Right. Okay. And this approach, is it open source? Is it something that people can apply to their own problems?
Yes, definitely. We have the code on our GitHub. And so we evaluated this specifically with TROPOMI or Sentinel-5P data, but in principle, it could work for any data fusion approach.
Mm.
Also with different numbers of modalities. So the standard data fusion scenario in remote sensing is with two modalities, for example, optical and LiDAR or radar. But for us, there's no such restriction. The model will automatically adapt to the number of modalities that you need.
Amazing. Okay. Well, thanks for giving us an overview. You've got a paper out at the moment,
Yes,
and
in-
where is that?
it's an IEEE JSTARS. Oh God, let me look up. I always forget what the full name of this journal is because it's very long. Um, it's the Journal of Selected Topics in Applied Earth Observations and Remote Sensing.
Right. Okay. And the title of the paper is
AutoMergeNet. Just a short title.
AutoMergeNet. Okay.
Yeah.
Yeah, that's easy to remember, isn't it? AutoMergeNet. Brilliant. Okay. So paper's coming out, code is out there, the solutions are being deployed and kind of refined in time. How does this tie in with everything else you want to achieve in your PhD?
Yeah, so it's now the last year of my PhD. Very happy that this paper's out because we've worked on this for a very long time. Now I'm thinking about how I can find a satisfying ending to this story before I wrap
Mm,
up. So we are working now on new project, specifically looking at the data we discussed earlier, and I also have some architectural ideas to further leverage the knowledge SRON mainly has about the problem um, in our approach. And we already looked a little bit at the data and we found only one small issue related to representation bias that we addressed in a workshop paper at the machine learning workshop
mm,
from ECML PKDD, where we found that our data set accidentally had a correlation between the number of missing pixels in an image and the label. So we had a lot of images without plumes with many missing pixels and very few images of plumes with a lot of missing pixels. So the models were learning how to count missing pixels
Mm.
a little bit. But it was fairly easy to solve, and we published also those techniques. So that was step one of diving into the data. And before the end of my PhD, I hope to at least have a better understanding of what causes this knowledge, this generalization gap between the test scores that we found and the operational
Mm.
case. Um, yeah, so fingers crossed for that.
Brilliant. Okay, well, exciting stuff, getting close to the end. Lots of interesting work coming in the pipeline as well. If people want to follow along your updates, which is the best platform?
Yeah, so probably LinkedIn or follow my Google Scholar. I also post updates about my research sometimes on my website.
Mm.
Specifically, I've written a few blog posts on machine learning for Earth observation, specifically for computer scientists, because when I did my first project with remote sensing data, I had to learn very quickly that it's not just like any other data, and there's quite a lot
Mm.
of extra knowledge even about file types, etc., that you need. So I wrote some blog posts about that
Mm.
that people can read.
Brilliant. Okay, I'll put all those links in the show notes. Once again, thank you for joining me today. Fascinating topic, and all the best with the final year.
Thanks.
See ya.
See ya.